Everyone, welcome to your Geometry Play Pause It for the week. This week we are going to be covering the very last part of classifying triangles, finishing the notes up from last class, and then getting our introduction into parallelograms. So go ahead and grab your notes, have your OMHS Play Pause It graded assignment open, and we'll get started. So here on these slides where it says last class, that's just a note for us to tell you guys that if you're following along with the notes, you're going to want to grab the guided notes from last class. Right? So we ended up here, most of us, some of us got a little bit further than this slide, but I figured I would just start here with everyone. This is the isosceles triangle theorem. So we know an isosceles triangle, we did learn already that it has two congruent sides. So there's a very special theorem that's pretty cool. It makes sense and it's really helpful. So the first thing it says here is that if two angles of a triangle are congruent, so let's write that. Two angles are congruent. You could essentially pick any two angles, but since this is an isosceles, it's these two here. Then the opposite sides are also congruent. So this side across from that angle is also equal to this side. So just to show you how easy this is and useful, if this is 2, what's x? Is 2. Is that easy? If the angles are equal, then the sides across from them are equal. Here's the second part of that working theorem, number 2 here, and the converse is true. So if two sides are equal, which we know they are in an isosceles triangle, right? Then the angles across from them are also equal or congruent. So if we know those two sides are equal, and let's say this is, I don't know, I'm just making it up, 40, it's not really 45, 45, then this one would automatically be 45. Obviously not drawn to scale, I just made that number up, but you can see how the theorem works. If the sides are marked congruent, then we know the angles across from them are congruent. Let's look at some examples. Here's the first one. So we know the angles are congruent because we have these markings here. So that must mean that the sides across from them are also congruent. So if this side is 7, then so is x. I always forget to remind you guys this in the beginning. I'm sure you know by now that, because this is a recording, you can pause at any time, catch up on any notes, try these on your own, for example, and then come back for the answers. So don't forget that. Let's look at, we can call this number 2. I'll do this number 1. So we have the angles marked congruent, so we automatically know the sides across from them are the same. Here is the converse of that theorem. Now we have the side lengths marked, so we know for a fact that the angles across from them are the same. So if this one's 75, then this one's 75. And then we could find this one, right? If we wanted to, because they all add up to 180 degrees. So that would be 30, right? If we wanted to. It looks 30 too, that's nice. All right, how about number 4 over here? So this is a triangle. I know it looks a little funky with the sides extended, just like this number 2 was. But we have the side lengths marked congruent, so we know that the angles across from them are congruent. So if this is 54, then this one is 54. So be careful. We still don't know x yet, right? We're just going to use the isosceles triangle theorem to help us find it. So we're kind of working our way through the triangle. So similar to number 3, we can now find the measure of angle x by subtracting these from 180. And I'm actually probably going to add these together first. I don't have a calculator. 108, right? So 180 minus 108. You guys check my math here. 180 minus 100 is 80. And then you take away 8 more, and it should be 72. Because this is a recording, I am going to grab my calculator and double check because I don't want to leave you guys hanging with any potential incorrect answer. So just like I do, you guys have a calculator at your disposal. It's 72. I'm right. Yay! So you can definitely check your work on that. X is 72 degrees. So we use the triangle isosceles theorem and the triangle sum theorem, both of those. Pretty cool. So here's another example. You have two questions here, A and B. They want us to find X and Z. So anytime you have a diagram, we're just going to look at it, right, and see what do we have? What do we know? Well, we only know one angle measure so far, so we can't find the other ones. But we do know that these two sides are equal. So that should trigger now in our memory that the angles across from those sides are also equal. So if this is 32, then this is 32. And similar to the last two examples we saw, now we can find angle Z, right? Because we know two angles, we can find the third. So we add these two together and get 64. And we take, why am I writing so slanted? That's so strange. 180 minus 64. I am going to grab my calculator. That is 119. Is that right? Angle Z does not look like it's 119 degrees. Not at all. This is a terrible, I just want to check my work. Hold on. I mean, the side length's really small, but no. Okay, so that's 32. That's 32. 32 plus 32 is 64. And 180 minus 64 is 116. 180. That's not much better. 180 minus 164 is 116. Okay, so I do apologize for that little mistake. I'm glad I double checked, but still, that's terrible. So this is not drawn to scale. I mean, it's good in the sense that it's an example where this can happen. I did not make this question up. So you can see that it does happen, not just by Miss Winslow standards, but people do it. So keep that in mind. You're not always going to have the perspective of the drawing to help you sort of validate your thinking. So we just kind of ran through the math again to make sure we did it right, and we did. So X is 32 degrees, and Z is 116 degrees. All right, two more slides from last class. So automatically, when I see this diagram, I just notice this outside angle here. Just kind of notice it. And remember, we do have an external angle theorem that might come into play. But let's look and see. We don't know any numbers, none. But we do know, actually, we do know this square here means 90 degrees, right? So I lied. We do know one number. We know 90 degrees. And then we also know that these two side lengths are the same. So if these two sides are the same, then the angles across from them are also the same. So that's X, this is X. So even though we don't know the measure of either one of these angles, because they're the same, we can still use the triangle sum theorem. So we can still say 90 plus X equals 180. See, I took these three angles and we're going to add them up to equal 180 degrees. You can always try it and see if it will work, right? Because these are the same variables and that's why it's going to work. Because now we're going to solve this basically kind of an algebra equation, right? We're going to combine like terms. So 1x plus 1x is 2x. And then to get x by itself, we're going to subtract 90 from both sides. 2x equals 90. And then divide by 2. And hopefully this feels familiar and you guys are remembering how to solve equations. We've done it here and there throughout our class, right? And look, it's 45 degrees. Each of these angles is 45. And if you don't know already, there's a special triangle and it's this one. It's a 45, 45, 90. 45, 45, 90. And when we get into trigonometry towards the end of semester 2, middle end of semester 2, we're going to do a lot with 45, 45, 90 triangles. They have some really special properties. So you can look forward to that. So we know X is 45 degrees. So now that we know this angle, we can definitely find Y. And it's up to you how you want to do it. I see two ways. Let's do it both ways. Why not? We know that X and Y are on the same line, right? Remember, that's a linear pair. Two angles on the same line that share a side. And those are always supplementary. They add up to 180. So we could do 45 plus y equals 180 and solve for y. And that is 165. So y is 165 degrees. The other way you could do this, if you saw this first, is kind of how I did. I saw this as an exterior angle. And remember that exterior angle theorem that says the outside angle equals the two remote interior across from it. Now our diagram looks so interesting now, doesn't it? So the exterior angle does equal 45 plus 90. And we can just confirm, and hopefully it should equal 165. And it does not. All right, so this actually equals 135. So then that's making me think, okay, what did I do wrong? Because we know that those are supposed to equal the same thing. So let me just check my math over here again, because I did this one in my head. Obviously, I needed more coffee today. And I need you guys. 180 minus 45 is 135. Okay, good. So we can always use the two methods to sort of compare and make sure we don't make any mistakes like I just did. 135. So I'm humble enough and I know that you guys understand enough that people make mistakes, right? And I do it, you do it, and it's okay. We learn from them. We use them as tools. We use our knowledge of the other methods to help us confirm things like this. So it's great if you have those two methods so you can sort of confirm your work. It is okay to make mistakes as long as we work through them, right? Okay, this says find the measures of the angles in the triangle. So find all the angle measures. And you can see we have these two side lengths marked. So we know the angles across from them are equal. So 11x minus 28 is equal to 7x plus 4. So sometimes you're not going to have an angle measure. You're going to have a mathematical expression. So we need to solve for x. So let's get all the x's together, subtracting 7 from both sides. And I'm just going to bring everything else down. And now keep getting x by itself, so I'll add 28. We get 32. And then lastly, we're going to divide by 4. So x equals 8. Once you have x, you can find all the angle measures. Let's just plug it in. So 11 times 8 minus 28. Oops, 88 minus 28. Get 60 degrees. And ideally, this one should be the same, right? Because they're supposed to be equal, and we set them equal. So when we plug 8 in here, we better get 60 degrees. And again, it's just another way to confirm we didn't make any mistakes. Sure enough. Okay, good. Now from here, you can certainly use the triangle sum theorem if you want to find that third angle measure. Let's do it both, or we can plug in x. Like I said, it's good to have more than one method. So you get 64 minus 4 is 60. So each of these are 60 degrees. If we used that triangle sum theorem, we would say 60 plus 60, right, minus 180. So that'd be 180 minus 120. 60 plus 60 is 120. And you do get the 60 degrees. So that's great to confirm. So what kind of triangle is this? All the angles are the same, which must mean all the sides are the same. So it's equiangular. We talked about this. Equiangular and equilateral. Equal angles and equal sides. And we're going to talk even more about those today. Before we do that, I do have a quick joke for you. Part of me is doing it in Play Pause It because I know you're going to roll your eyes at me. Because I know some of you don't prefer my jokes. Why can't Elsa play hide and seek? Why can't Elsa from Frozen 2 play hide and seek? And the answer is because she'll show herself. Oh my God. I hope you're laughing. My husband made this joke up. Okay, because my daughter Lily, my 6-year-old, she tells the joke from Frozen 1 all the time. Why can't Elsa have a balloon? I think I told you this. Because she'll let it go. Well, then my husband was like, well, isn't there one for Frozen 2? And he made this up, and we cannot stop laughing. I'm going to tell everybody I know. You should too. Why can't Elsa play hide and seek? Elsa from Frozen 2. Because she'll show herself. Okay. Whew. Let's refocus. Tell your parents you're doing geometry, which we are. So let's get into polygons, which is going to guide us into our first polygon of parallelograms. So the definition of a polygon, and I know you guys have been studying polygons for literally ever. My daughter in kindergarten is studying polygons. So just to kind of give it a formal definition, you can add this to your notes. It's a closed shape. So there are no openings. And there must be straight edges. So a circle, for example, is not a polygon. That's pretty much it. It's a closed shape with straight edges. So let's look at some examples. Is number 1 a polygon? Yes or no? What do you think? I think yes. It's closed. See, there's no breaks in the sides, and they're all straight. They're not curved. Number 2, this is not a polygon. Some kind of shape, but it's not a polygon because there are curved edges. It's closed, but the edges are curved, most of them. Number 3, yes, a star is a polygon. It's closed, there's no openings, and the sides are straight. Number 4, nope, curved edges. And number 5, no, it's not a polygon because there's a break here. Yes, the edges are straight, but it's not closed. So in order to be considered a polygon, you have to be closed and straight edges. So these, and again, I feel like this is going to feel like a little bit of repetition as well, but we do need to recall these as we work through this unit in geometry, the names of these polygons. I bet you can pause this recording and fill in almost all of them and come back for the answers. I'm going to grab my text tool and type this for you guys. So 3 sides we know is a triangle. 4 sides, we're going to call it a square. For now, let's add this. It could be a quadratic. Or not a quadratic, a quadrilateral. I was thinking of solving quadratics, which we're going to do today as well. Quadrilateral. You guys know that we can have multiple types of quadrilaterals. Anything with 4 sides. So a square is one example. There's rhombus, trapezoid. So there's all kinds of 4-sided shapes. 5-sided shape. Did I spell it wrong here? Thank you. Thank you, spell check. 5-sided shape is a pentagon. I always think of the building. Side note, my stepdad actually was a first responder to the Pentagon on 9/11, so we hold that very dear. He just retired recently as a fire, oh my goodness, battalion chief of Alexandria City. So little tidbit there. A 7-sided shape is a heptagon. An 8-sided shape, always think of an octopus. It's an octagon. You can see most of these have gon on the end because they are polygons, many sides. Poly meaning many. 9 is a nonagon. That might be a new one for you. 10 is a decagon. I feel like I'm missing 11. Do you guys have 11 on your paper? I don't have it here. I'm gonna put it here. 11 is a, okay, so there's a few. 11gon doesn't really have a special name, and sometimes you'll see it called, oh gosh, how do you spell it? An endecagon, that's it, Endecagon. Yep. And 12 is dodecagon. And any sided shape is an n-gon. So if you have like, you know, a 27-sided shape, we would just call that a 27-gon. But in our class, we're mostly going to be working with 1 through 12. And we are going to need to know the names because you might come across a question that says something like, you know, there's no diagrams and it says, find the angle measure of the octagon. So you need to know how many sides does an octagon have? Oh, it's 8. So we are going to need to remember these names. So there's two ways, actually there's a few ways to classify polygons. And I have this picture here and it's going to make a lot of sense in just a minute when we talk about the definition of these things. Oh, where's my pencil? There we go. So a convex polygon is actually when you extend the side of the polygon, excuse me, they do not intersect the interior. So let's write that. If you extend the edges, I should type this, of the polygon, the sides do not intersect the interior. A convex polygon is one that you might think of like a square. So let me show you what I mean about this side business. So I have a square, and if I extend the edges, so let's say I extend this edge, see how it doesn't go on the inside of the shape? No matter what edge I extend, it will never go inside the shape. That's the definition of a convex polygon. See, I'm extending each of these side lengths, and those red lines do not go inside the shape at all. So no matter what kind of convex polygon, that's what you're going to get. Here's another example, a triangle. If I extend the side, any of these side lengths, those red lines do not go on the interior of the shape, the inside here, none of them. So those are convex polygons. Let's look at concave. So it's actually just the reverse. If you do extend the edges of the polygon and the sides do intersect the interior, then you have concave. So you can write all of that out. You could say not convex. Let me type it for you since I can. We can get these in your notes, but you will not have to memorize these definitions. I'm going to show you visually how to tell, kind of like I did there. Okay, so if you extend the edges of the polygon, the sides do intersect the interior of the polygon. So let me show you an example. Here's one. Of course, I'm freehanding it. Okay, there we go. So now it is a polygon, right? It's closed. It has straight edges. Let's see, if I extend this side, okay, we're good, we're good. But look what's going to happen if I extend this side. It goes right through, or even this one. It goes right through the center of that polygon. So it is concave. So I love this name because look, it kind of looks like a little cave. That's why I have a picture of a cave here. Here's an example of a concave polygon. Any polygon that kind of has an opening. And that makes sense if you think about it, because that opening that's kind of going inside the shape is going to cause those edges to go inside the shape. So let's look at some more examples. Here they are. Number one. So number one is a polygon. It's closed and it's straight. And if you were to extend any of these edges, it does not go inside the shape. So this is convex. And if you kind of look at these, which one looks like a cave? Which ones have an opening? Yep, this one. This is concave, but it's not a polygon, right? Because it has that curved edge. This one is a polygon. They're all straight. And look, it has that indentation, if you will, because if you were to extend this, it would go right through the shape. So this is also concave. The triangle we saw is convex. Convex, all these sides are going to be on the outside of the shape. And the arrow is concave. You kind of have two little caves here. And you can always do the test. You can always try to extend an edge, and if it crosses through the shape, you know it's concave. So we have convex and we have concave. We can also classify polygons from their sides and angles, which we talked about already with triangles, but we can also do it with polygons. And so a regular polygon is one that is both equilateral and equiangular. It has to be both. And it's kind of funny that it's called regular, because I feel like it should be called special or something, right? So a regular polygon is equilateral and equiangular. So here's an example. All the angles are the same, all the sides are the same. This is a regular polygon. It's a regular triangle. This word regular. And we're going to need to know that term because you guys will see questions and it'll say, like, for example, find the side lengths of the regular octagon. So that buzzword regular will tip you off in your brain and say, oh, it's regular. That means it's equilateral and equiangular. So just a quick review. I know we talked about this with triangles, but this is for all polygons. Equilateral means equal sides, lateral meaning sides, and equiangular means equal angles. So this is the best definition ever. Irregular polygons, guess what? They're not regular. That's it. So it can be one of these, but it just won't be both or neither. Basically, if it's not regular, it's irregular. So let's try some examples. What kind of polygons are these? Let's label them as much as we can. So here we have all side lengths are marked congruent. So we know that's called equilateral. And it looks like we don't have equiangular, right? Because these are congruent and these are congruent. So we can't say equiangular, which means we can't say regular because it has to be both. And then, okay, it's four-sided, so we call that a quadrilateral. And I think that's all we got right there. They don't tell us anything about the sides being parallel or anything like that. Okay, number 2. It's not equilateral, right? Because 4 is not the same as the 5s. Let's use this information to see if we can figure out anything else. Okay, so these two angles are equal because they're across from the sides that are equal. Yeah, that's it. So we would call this irregular triangle. It is a polygon. It's closed. These are both, these are both convex. There we go. All right, here's an example. Show this is a regular polygon. So again, we know this word regular means equal sides, equal angles. So if this is regular, then these would have to be equal. So let's set them up to be equal. Now, if I recall correctly, I set this up on purpose to not work. So let's see what happens. We want to try to solve for x. So we're going to get all the x terms together. So let's move the x squared over with the x squared. And let's move the 3x over with the x. So these will go away also, and we'll have negative 2x equals, plus 2 equals 0. Okay, now we're going to subtract 2 from both sides to get the x term by itself. Oh, you know what? This one does work. Okay, good. That's good. Divide by negative 2. and x equals 1. So let's plug it in and see what happens, because they want to show that it's regular, which means that the sides have to be the same length. So we'll plug in 1, and we get, what is this, 4? 1 plus 1 is 2, 2 plus 2 is 4. And then here, plug in a 1, and you get 1 plus 3, which is 4. Woohoo! So the side lengths are equal, which is good. They should be, right? We set them equal and solve for x. So it's funny, we can't really show that it's regular because we can't show that the angles are all the same. So, if this was a real problem, you would email me and say, it's not possible. But since we're here doing it together, we do know stop signs are congruent, all these angles. So we can mark those to show that they're congruent. And then that would be a regular polygon. All right, so now we're going to talk about one more definition. I think this is the last definition of the day, the central angle. And it's exactly what you guys think it is. It's an angle whose vertex is on the center of a shape. Typically, we're going to talk about central angles of circles. So let's just write that definition. It's an angle whose vertex is the center of the shape. So when we get to our circles unit, which is going to be towards the middle of semester 2, we're going to have quite a few circle formulas, and this is going to be one of them. So I'm actually not going to bombard you right now with the central angle formula because we're not going to use it until semester 2, but we will see some central angles in this unit, so I just wanted to introduce it to you guys. You aren't going to have to find the measure of it though. But it's cool because it makes sense, right? The vertex is on the center of the shape. Central angle. Again, when we get to circles, we're going to see all kinds of angles. We're going to see angles that are on the edge of the circle. That's an inscribed angle. So this is a recall. Scalene, isosceles, and equilateral. Remember, scalene triangles have what? All different sides. The sides are scattered. Isosceles, I love, someone in my second class said isosceles. We have two eyes. Two eyes, so two sides are the same. I love that. I'll never forget that. And we know equilateral, right? All three sides are the same. So now let's get into parallelograms. Isn't that photograph amazing? This is in Hamburg, Germany, and that's an actual building. It's off of a dock, so to speak, but it's a building. It's not a ship, it's a building. And it's a parallelogram. Could you imagine being the architect of that building? You would have to know an insane amount of geometry. So cool. And I'm guessing if we were together, you'd be filling the chat box and telling me that a parallelogram has what? So it's a polygon, right? And what's a special polygon? It has four sides, so it's a quadrilateral with both pairs of opposite sides are parallel. Hence the name parallelogram. So quick sketch here for you to show. Remember, we use these little arrows to show lines are parallel, and these are also parallel to each other. And I'm using two tick marks, two arrows, because they're not the same as these. You also might see it written with triangles. So let me do like this instead of the arrows. Oh man, so those are markings that the sides are congruent. I'm sorry, parallel, parallel, parallel. So parallelogram has both pairs of opposite sides. And there are some special theorems that go with it, and a lot of these make sense, and I know that a lot of this is going to be a review for you. So if a quadrilateral is a parallelogram, then we have an if-then here, our good old conditional statement. Both pairs of opposite sides are congruent. And they look congruent. There's the markings. I don't really think I have to show you the example for this because I marked the picture, but I'll do one here. We could say QP is congruent to RS. Those sides across are congruent. And QR is congruent to PS. All right, number 2, I'm going to change my color. I don't love writing in red. Okay, both pairs of opposite angles are congruent. Opposite angles are congruent. So Q and S and P and R. Angle Q is congruent to angle S, and angle P is congruent to angle R. Number 3, consecutive angles are supplementary. Remember, consecutive means one after another. So here it's supplementary angles are Q and P. And you know what's so cool about this? Because we learned about parallel lines and transversals. If this is a parallelogram, these are parallel, right? And look, this is like a transversal. So we know that consecutive angles are supplementary, just like from before. So angle Q plus angle P equals 180. The two that are right there. Angle R and angle S, oops, equals 180. Excuse me. And the other ones as well. Anyone that are next to each other, not across from each other. And then lastly, diagonals bisect each other. So remember, that means that they cut themselves in half. So that means this would equal this, and this would equal this. We could call this O, and could say QO is congruent to OS. And PO is congruent to OR. So bisect, diagonals bisect, meaning they cut themselves in half. So each of those little pieces are congruent. Two more examples to kind of work through some parallelogram problems. So here they give us the diagram, and we're going to label it. EJ is x squared minus 4. JG is 3x. And it wants to know the entire thing. So because we know it's a parallelogram, we know that the diagonals bisect. So those two pieces must be congruent. So let's set them congruent. So let's get all the x's together. Now this is something we have not done this year yet. We have 3 terms, right? 1, 2, 3. And 1 is a square term. Do you guys remember doing this towards the end of Algebra 1 last year? This is called a quadratic, and we have to factor it. Because there's a squared, there's going to be 2 possible solutions. So remember, when we're factoring, we're trying to make it look like this. And there's a few ways to factor. When the coefficient is just 1, we can kind of guess and check. So we'd have x's here, right? And then we got to think of the numbers to put here. So if you had me last year, you know, we made Ma charts. I call them Ma charts. So it needs to multiply together to give you the first times the last. So -4. And then it's got to add together to give you -3, hence the Ma. Multiply together to give you the first times the last, and add to give you the middle term. So we're looking for 2 numbers that do that. So let's look at the factors of -4. It's going to be -1 and -4. Nope. +1 and -4, or -1 and +4. So look at these 2. I mean, we could do 2 and 2 if you want also. But we want to pick one of these pairs that is going to add to give us -3. And it is this one, right? 1 minus 4 is -3. So that's what we put in these spots. 1 and -4. So I know that was kind of like a very quick lesson on factoring, and we're not even finished yet. but we will do more. And if you guys feel like you need some extra work on factoring, just let me know and we can spend some time on it, or I can definitely send you some more extra resources. But we are going to start to see it. So now we have these two possible solutions. So we're going to set each of them equal to 0. And we have two tiny little math problems. So x equals -1 and x equals 4. So we're going to look at these two and see which one makes sense. Well, if x is -1 and we were going to plug it in up here, we'd have a negative value, right? You can't have a negative length. So that's an extraneous solution. It's not one of the solutions. X equals 4. Let's plug it in. 4 squared minus 4, that's 16 minus 4, that's 12. And 3 times 4 is 12. Perfect. They're both the same. That's what we would expect. And then it wants to know EG, the whole thing. So 12 plus 12. EG is 24 units. Woo! That was a honker of a problem. It was a good one. So we used our knowledge now of what a parallelogram is to know that those diagonals bisect, and then we recalled how to factor. Here's our last one. What is the measure of DAB? So we're looking for this angle. So we know it's a parallelogram because of these markings. Look, and we have two pairs of opposite sides that are parallel, this one and this one. So that tells us immediately it's a parallelogram. So all of those properties we learned go into play, which means consecutive angles that are right next to each other, are supplementary. So we call this x. So 96 plus x equals 180. Subtract 96 from both sides. X equals 84 degrees. That's it. And you're done. You guys, thanks for hanging in there with me. I know this is a little bit longer one than usual, and there's a lot going on, but I hope and I feel like most of the beginning stuff was kind of review, right? Like the different shape names and things like that. So I will see you guys on Thursday to continue our parallelogram discussion. Please look on your plan for today. There are two important things, an item about a survey and then an item about if you're missing any emails from me at all. Bye, everybody.